All right, so hello and welcome to Algorithms Live. And this week I'm going to be covering this problem type called 2sat. So it's 2 satisfiability. And we'll be going over how to set up problems for this. You'll see in a moment this technique is a lot like network flow in that you just set up the graph or you set up what you're trying to solve and then you run a standard solver that you write. So I'm just going to go over like what the base problem looks like. Give a little bit of how this thing works, try to give you like a conceptual understanding of it, and we'll dive through all that. And then we're going to do some problems. So I've got 2 problems in mind. One we'll just talk about conceptually, and I recommend you code that one. The other one, I'm going to run through the solution a little deeper, and then I think I'm going to try coding it. So we'll see if I can get it working, though. So I'm actually live coding this one this week, so I don't know how easy it'll be for me to solve, but I'll give it a try. All right, so we'll dive right in. One of the things I'd like to talk about first is everything I'm going to do today is based on this thing called propositional logic. So a proposition as a statement can be true or false, not both. And you can kind of chain these things together. When you're dealing with propositional logic, you typically have these variables, p or true or false. So you'll have things like p or q. So we have this little wedge, little v symbol for or. My and is going to look like this. This is a wedge symbol. If I say P or Q, but not both, I make this circle and kind of a plus sign. So that's saying P is true or Q is true, but both of them can't be true. And also there's this negation symbol out in front of my propositional variable. I'm saying that not P is true. And so that's just a notational thing. You can read more about this if you want in Rosen's Discrete Mathematics. You can, or just find a discrete book. Some of the notation changes depending on the text you're reading, but this is the notation I'm going to follow for this video. So you can map it to your favorite notation however you want. So let's talk about sat. So we take these Boolean expressions and we have this problem called sat, or satisfiability. And the only thing you're dealing with here when you deal with sat is you're just given a compound proposition. So it doesn't really matter what the proposition is. Here's an example of one such proposition. I can put them together. And you can combine ands and ors however you want. Ands typically have higher precedence than ors, so that's why I'm using parentheses. But it looks something like this. And what you want to do is you want to just find truth values for P1, P2, and P3. So just set each one to true or false. And when you resolve these ands and ors together, you either get true or false. You want to see if you can make this true. So satisfiability is all about trying to make your compound proposition true. Can you figure out how to solve it? And generally, sat is NP complete. So you're not going to find an efficient solution to that. But there is this thing called ksat that we're going to talk about. I'm just going to define what ksat looks like. And so what that means is if we take, what I have here is something called conjunctive normal form. And what I mean by that is we have a bunch of disjunctions, which are or statements, stuck together with conjunctive statements, so ands. So conjunctive statements are ors. And so if you have something of that form, and you can negate any of these propositions, that's fine. But if they're just stuck together with ors, and each of these disjunctive statements is stuck together with ands, you have conjunctive normal form. And if you want to know what k your ksat is, well, you look at the disjunction that has the most variables in it. So if I go up to k, and whatever that most variable is, that defines what the ksat is. And so the cool thing here with this compound proposition that we're given right here is this is a 2sat proposition, because none of these disjunctive statements are bigger than size 2. They only have 2 propositions in one of them. And so this special case of SAT, this 2-SAT case, is a lot easier to solve than other K SATs. So that's good news for us. So let's just figure out how to solve this one. So I just have this compound proposition. What I have to do is I have to make this whole thing true. So I'll just make choices for the variables. So I'll pick P1, maybe set that to true. P2, set that to true. P3, set that to true. And so we get 3 different variables in this form. And what we'll do is we'll just play around with this. Well, what we get here is true and true, true or true. True or true reduces to true. Then we get not true, so that's false, or true, that's true. False or true is also true. And then this last one, we get not true, which is false, ORed with true. So false or true turns into true. And so the goal is you want to get every single one of these to be true because they're all disjunctions together. So true and true and true is the only way you get true. So this whole thing resolves out to true. So that's how you can just work one of these equations. So one of the satisfying pieces to that compound proposition is just set everything to true. We could have just as easily set P1 to be false. You can play around with that and we'll still get the exact same truth value here. So there can be multiple solutions that exist and that's perfectly fine. All right, so let's talk about our goals for 2-SAT. If we're going to solve 2-SAT, is we're going to be given a compound proposition and we're assuming it's given in conjunctive normal form. So our goals here are we want to know, is it satisfiable? So can we satisfy this statement? And if we know the answer, what are the values for P1, P2, P3, or so on? So what values work to make it satisfiable? So that's kind of like a constructive problem. Sometimes you'll even want the lexigraphically first solution for the satisfiability. But usually it's one of these things where you just pick a truth value, you run the whole 2-SAT instance, and then to see if it worked or not worked, and use 2-SAT as an oracle. So that's not too hard, but there's also a way to pull out any answer or some answer, not necessarily a specific one. And the last thing we want to do with this is we want to know how to model problems as 2-SAT. So the best part about 2-SAT is it can be used to solve a number of different problems. So it's very similar to max flow problems or linear programming problems. It's all about the setup. So what you're trying to do with 2-SAT is just take whatever problem you have, reduce it to this conjunctive normal form, and then solve that piece. So that's typically how I approach 2-SAT problems and the pattern you're going to see. Okay. So let's talk about what can happen in terms of figuring things out. So let's say we have a bunch of propositions. So we have something like P1 or P3. And let's say we know that not P1 is true. So not P1 is the same as saying P1 is false. It's saying this is false. So if you knew that not P1 was true, and you knew that P1 or P3 is true, you can actually deduce that P3 has to be true. So you'll have something like this, P1 or P2 or P3, not P1, and you can just write out therefore P3, something like that. So one way you could state this in plain English is like, you know you have an apple or you have an orange, but you know you don't have an apple. So then you can infer that you have an orange. So it's just a logical deduction. And the cool thing about this is it works on both sides. So let's say let's say not P3 was true, then you could deduce P1. So That really just has to do with the fact that this is commutative for or. So this rule just ends up being the same. But it's important to realize that for an or statement, there's two things you could possibly deduce. You assume one, you get the other, back and forth. And this has a name. It's called disjunctive syllogism, where that's the name Rosen gives it. And I just want to talk about this relationship with implications. So you can actually think about these instead of as ors, and then like if you knew something was true, deduce that other piece, you can think of everything in terms of implications, which is going to be really useful for us. So the way I'm going to think about it in terms of implications is I'll do P1 or P3. There's a couple ways you can rewrite those. And if you write a truth table for these, so you could go to the Rosen book and figure out how to do that if you're not familiar. But these are equivalent statements. So if you know P1 is true or P3 is true, then you know if not P1 is true, you can deduce P3, which is exactly what this is kind of saying, right? And if you can also take the contrapositive of that, if you know not P3 is true, you could deduce P1. So if not P3, then P1. And these two things are the contrapositive. So this is the contrapositive of this. This is the contrapositive of this. So you can take the contrapositive. So the neat thing here is this or gets you two implication statements. It's important to have both of them because you could, if you knew that not P1 was true, you're able to deduce P3. If you don't have both these implication statements, then you don't get the full information. You can't detach everything you have. So let's just look at that detachment rule. So if you have P implies Q at any point, and you know that P is true, then that's good enough to deduce Q. So this is called modus ponens sometimes, or detachment rule, or something like that. And so that's how we're going to approach things here. We're just going to look at these propositions. We know that if something is true, then we can infer the next thing. Something is true, then we can infer the next thing. So we can get an inference graph. Or I think maybe the name is implication graph. So we look at these logical implications like this. And all I'm going to do to make a graph is every time there's an implication that I can form, I'm just going to add it to my graph. So for all valid inferences, so for all valid P implies Q that I could possibly form, I make an edge. And what are the nodes? Well, the nodes look like this. If you have a variable that can be true or false, we're going to add both that variable and its complement. So that's how we're going to be thinking about these. So we're making a graph for all the propositions. So PI is true is this node, and not PI is true is this node. And that's how we're going to make this implication graph. It's okay. So let's just build one from scratch. We solved that two-sat instance just by guessing, but let's try to do something a little smarter. So if I look at the original two-sat thing that I wrote out, I wrote something like this. And I get these disjunctive statements. Okay. So for every single one of these ors, we can turn them into implications. So I get P1 implies P3, not P1 implies P3, not P3 implies P1. I can do P1 implies P2, not P2 implies P1. So again, you just think of like if one thing is certain, what can you infer? That tells you how to get the implication. You can also do P2 implies P3, and not P3 implies not P2. And so those are all my implications. And so now I can make a graph out of this. So I'll write out my nodes. So I'll have P1, P2, P3. And I'll have not P1, not P2, and not P3. And those will be my nodes. I'm going to make this graph a little more colorful. So I can do not P1 goes to P3. I do not P3 goes to P1. I do P1 goes to P2. Not P2 goes to, oh, I guess this is not P1. So I did make a mistake. But very good. Go out to here. And I go out to here. So I get a graph looking like this. And so I want you to make an observation about this graph. If you decide to take a node, so we're either going to take a node or not take a node. And that holds for all these pairs. So we're either going to take P1 or we're going to take not P1. So in other words, you can assign P1 to be true or you can assign it to be false. But the cool thing about this implication graph is if I decide to take node Pi, so if I say Pi is definitely true, or not Pi is definitely true, then anything that can reach, so I just follow the chain of implications, must be true. And that's just from infinite rules. We can use that modus ponens rule. So if not P3 is true, then not P2 has to be true, then not P1 has to be true, and you can just follow this whole chain of implications down. So one cool thing is you'll notice that these things chain together, and you can just follow the chain down for reachability. So if we took not P3, for example, right here, we follow the implications, go to P1, go to P2, go to P3, then we know P3 is true. So we know that not P3 is true, and we know P3 is true. If both those things are true, then we have a contradiction. So we can't possibly take not P3. That's the kind of cool thing about this implication graph. You could do like a depth first search and just figure out what you could reach. So we know right now if we take not P3, then we're going to have a contradiction through this chain of inferences. Another interesting thing I want to point out is that this statement right here is logically equivalent to just saying P3 or P3. So if one can reach the other, like if P3 can reach not P3 or vice versa, then it's basically a way of forcing a variable to be true, because you don't want to have that contradiction. So we know that P3 can never be true, and we know that this statement right here is just P3. So P or P is P. So it's, I think, idempotent law, if you know your logic rules. So it's kind of a neat thing you can do is anytime you want to force a variable, you actually just add. So let's say you want to force P, then you just want to add P or P to the implication graph, which means you just want to add not P implies P to the implication graph. So if you're able to do that, you can force P. If you want to force not P, you just add the converse here. And so that's what that looks like. And you just add this to the graph, everything is fine. Okay. So let's take a look at our graph and think about how we find the answer. So I drew this graph here. It's not like drawn in a very clean way. I kind of have crossing edges. It's a little hard to see what's going on. So I'm just going to redraw it here. So I have not P3. And if I redraw it, I have not P2. I have P1. I have P2. I have not P1. And I have P3. Something like this. And I can just draw the edges that I had. These are the implication edges. Okay, so how do we find the answer? Well, one of the things you'll notice is if I look at the sync node, or a node that has out degree 0, first off, this graph is a DAG. That's pretty helpful. And if I look at P3, it can't reach anything. So I could just like set this to true and not really care. So I could say, oh yeah, P3, it's totally true. And there's no consequence for making that choice, which is really nice. And then I could remove it from the graph. So just remove it from the graph. And then I have two nodes like this. Well, I get a choice here. I could do not P1, or I could do P2. Maybe I pick P2, and I set that equal to true. And then I remove that from the graph. Like, so maybe remove that node from the graph. I can either pick not P1 or P1, but in this case, maybe I pick P1 and that's true. Or I could have picked not P1 and that would also be true. And you'll notice I end up with something that's satisfiable. So what we're going to do is we're just going to go in reverse topological order to find the answer. If I ever run into a situation where I've already taken something, so like I've already taken P1, so now I go over to this not P1. If I've taken the complement already, then I don't take it. Otherwise, I can take it. And I keep doing this taking. And any topological order will get me satisfiability of this graph. So what you do is just run this in reverse topological order. You pull out the answer this way. So you're just like basically greedily taking every single proposition in reverse topological order and then assigning the truth value. Okay, so there's a few things you should probably notice about this with the way I did this. First off, what if not a DAG? Right? It's not guaranteed to be a directed acyclic graph, right? It just happened to be with this example that I showed you. So it could easily be something that's not a directed acyclic graph. And then not every compound proposition is satisfiable. We could have something that has no way to be satisfied. So we just ask ourselves, when is the compound proposition not satisfied? These are good questions maybe you should be asking yourself. Okay, so I'm going to write one out. I'm just going to write one that isn't satisfiable. And we're going to see what happens. And this one's also going to have cycles. So I'll do P1 or P2. I'll do not P2 or not P3. I'll do not P1 or P3. And the last thing I'll do is P3 or not P2. Those are my statements here. So I can just write out the implications. Something like that. I can write out P2 implies not P3. I can write out P3 implies not P2. Something like that. So I get something like this. So I can draw out my graph. So I want you to just see what's going on here. So it's a 3-variable graph. So you always need 2n nodes where n is the number of propositions. So not P1 implies P2, not P2 implies P1. P2 implies not P3. Not P2 implies P3. Oh, I did something backwards here. So it's P2 goes that way. That way. Okay, good. P1 implies P3. And we have that one going this way. And not P3 implies P2. And P2, oops. P2 implies P3, something like that. You can draw it without edge crossings. That's probably better. Okay, so what you'll notice with this graph is if I take not P1, I can follow a chain of implications. So let's take this. I can go down here. Actually, let's use a different color. We'll do red. That's probably good. We'll start here. We'll follow the chain of implications here, follow it here, follow it here. And then you get to P1. And I can also go from P1, follow a chain of implications. That was a bad choice. How do I get to P3? Unless I deleted an edge. Well, P2 can get to not P2. That's probably the best way of looking at it. Yeah, I can get to not P2, whoops. So we can get from here to here. And then not P2 can get to P2. Or I thought so. Maybe I should write out the top sort here. Something clearly gone wrong. This one might be satisfiable. Picked a bad graph. P1, not P2. We'll just put these three in the cycle. P3. So it looks something like this. And then the other three are also in a cycle, so not P1, P2, not P3. This one will be easier to see if there's a cycle. And then there's some things I'm missing. So P2 goes to P3. Not P3 goes to not P2. Four, 5, 6, 7, 8. Yep. So they are in separate, strongly connected components here. So this one is satisfiable, which for some reason I thought it wasn't. But one thing you'll notice is we can basically group them by the strongly connected components here, because if P1 is true, everything it can reach also has to be true. So P1 can reach everything else here, P2, and then we could also have something here where P1 can reach everything. So that's a problem. It's forcing something. So if the graph is not a DAG, what we can do is we can just compress these nodes into strongly connected components and then basically group them into clusters like they're a single variable, like saying that if I take something in this group, then everything in this group has to be taken right away. So what happens is if you're doing a two-sat problem and P1 could reach P2, not P1, and not P1 could reach P1, Well, that's the same as saying you have P1 true and not P1 true, which is a contradiction. And if you have a contradiction in your compound proposition some way, then you end up having this problem where you can't satisfy it no matter what you do. So all you're doing with this implication graph is you're looking for contradictions. And it's a very easy check now, because we just have to check if P1 can reach P2, not P1, and not P1 can reach P1. So you can do that with a DFS, or you could compute the strongly connected components and do it very quickly. So here's our algorithm. So our first thing is to run SCCs. So we get all the strongly connected components of the graph. The second thing is see if whatever PI is can reach not PI, and vice versa, which you just check if they're in the same strongly connected component. And that's for all PI, or for all I. And then the last step is if it's satisfiable. So this doesn't hold for any of the propositions, so you don't have a single contradiction. Then what we can do is we can go through this metagraph. So we have our metagraph right here, just like we were doing in the strongly connected components episode, and just go in reverse topological order and extract these nodes. And so for this strongly connected component, what we could do is we would just say P1 is true, not P2 is true, and then P3 is true. And then if anything in a later strongly connected component conflicts with something that's already been taken, so we just save these flags on what's already been taken, then we don't take that entire node in the strongly connected component. So you'll notice a satisfiable statement here is P1 is true, P2 is false, and P3 is true. And so you just get those three pieces and then you plug them into this equation, and you'll see this compound proposition will actually resolve to true. And you can just do that by doing a little bit of graph theory. So the thing you could probably ask yourself, so the last thing I want to say is if we're going in reverse topological order, I just want to reemphasize that if you run Targens or you run any any strongly connected components algorithm, it gives you a topological order. So just make sure to go in the reverse order of when the components were found, or in the order the components were found, depending on the algorithm you're running. And you don't have to run a separate top sort to pull out the answer. So the question you might ask yourself is, does this always find the answer? Because this is kind of a greedy algorithm. And so the thing you would need to show, so this piece right here is trivial. So let's say S is the chosen set. And so chosen set is we either added P or not P to that set. And we have to put all our choices in here. So it's trivial to show that PI is not in our set, or not PI is not in our set. The reason that's true is our algorithm doesn't take something if it already has the contradiction. So at least one of these has to not be in our set. So the only thing we need to show in terms of our algorithm is PI is in our set of choices. So PI is true, or not PI is true. And so that's one thing that you can work out to show that when this algorithm completes, you're not going to get this case where you didn't take something, one or the other. And I don't think this is too hard to prove. So I'll let you think about that. Just think about the algorithm, how it's going in reverse topological order. And it's probably pretty easy to do with a proof by contradiction. You just walk through things and just show. So it's like the algorithm doesn't hit this P of I. So find some arbitrary node and then show that it definitely hits it. So you end up getting this nice proof by contradiction that way. Okay, so this algorithm will work, and that's how you can pull out the answer. It won't pull out necessarily the lexicographically first one, but it will pull out an answer for sure. Okay, so that's 2SAT. That's how you run 2SAT and use it to solve a problem. So let's talk a little bit more about 2SAT. So right now we get things in these disjunctive normal form. Something like this. I want to talk about how to add other pieces. So one of the other pieces that we could add is we could add XOR. So exclusive OR is one or the other, but not both. So something like this. You can always add XOR to your conjunctive normal form and it will work out. The reason is you could write it as a subpiece of the conjunctive normal form. So if P or Q is true but not both, that's logically equivalent to saying P or Q, not P or not Q. And again, you could draw a truth table out to this. So we end up getting a statement like this. It's just two disjunctions added to, like, anded to the rest of our implication, our conjunctive normal form. And if you think in terms of the implication graph, you're just adding 4 edges for every XOR. So you add the 2 edges for this OR, you add the 2 edges for this OR, and you get XOR. You could also do bidirectional implication. You can set P and Q to be the same thing. And that's because not P is the same as this XOR. So you could just rewrite it in terms of the XOR code, or you could just set it up this way. You'd have P implies Q, Q implies P. So those are edges in our graph. Not P implies not Q implies P. And so then you have a way of setting values to be equal to each other. So this will set them to be opposite. This will set them to be the same. And you can just add that to your implication graph. It's a very nice trick. So one of the things you can do is you can actually, if you have a 2-coloring problem, so given a graph, see if you can assign each vertex a color so that no 2 vertices that share an edge have the same color. And you can only use 2 colors. You can actually model if something is 2-colorable as a 2SAT problem. So that's a really good exercise for you. And you can do that using this XOR here. So you can use XOR to think about that problem, model 2-coloring as 2SAT. It's a very good exercise that you can try on your own. And see if it'll make sure you understand XOR really well. Okay, so that's the gist of XOR. Let's talk about, we already talked about how you can add a forced edge. You just add P or P. And that's pretty much the main things you can do with XOR in terms of patterns. Okay, so let's talk about some problems. So we updated OneNote, so I'm actually going to switch over to this graph theory style paper and see how well this works. Okay, so let's talk about the first problem in the blog post. There's this problem called illumination, and I'm just going to talk about how this problem works. So what you have is you have some lamps. They can illuminate up to R cells. So they tell you what R is. So in this case, R is 3. So they illuminate the cell you're on and all cells in either of these directions. And they're in this haunted house. So they can illuminate either vertically or horizontally like this. So you can turn them vertically, you get something like this, or you turn them horizontally, you get something like this. And the important thing here is you don't want a cell to be illuminated twice. So let's say I had a cell here and a cell here. Then if my size was 3, it'll illuminate these, it'll illuminate these. And these cells were illuminated twice, so that's a problem. The exception, though, is if a cell is illuminated in an opposite direction to some other cell, something like this, and they cross like that, that's fine. So it's a weird quirk in the problem that they allow. And so this problem is called illumination. All right. So when you're working a two-sat problem, the main tip I'd say is find your variables first. So find what you want to be your variables. So for this problem, the thing I'm going to be, my variable, I'm going to say p sub I is true if whatever lamp I is vertical. So did I set the lamp to be, so the lamp has to light up in this problem. Did I set it to be vertical lamp with illuminating this way? Or if pi is false, then lamp I is horizontal. And so I get this case. And so that's how I can model this problem. So I basically have two states. So instead of thinking of it as true and false, I have like vertical and horizontal. And it just makes things a little bit easier. So once you have your variables, you can start thinking of what your disjunctions are going to be. So your variables model your state, your disjunctions model your rules, basically, how you're going to set up the constraints to make this possible. Okay, so we have P1, or let's take a look at what could happen. So let's say I have lamp 1 and I have lamp 2, and they're within striking distance of each other for some reason. So we know that if we put them both horizontal, then they're going to overlap. So what we do in this case is we want to ensure that one of them is vertical or the other one is vertical in this case, right? So they don't have to, and they both could be vertical, that's fine, but at least one of them has to be vertical. And so the easiest way to enforce that is just do P1 or P2 as my rule. So in this case, they could both be vertical, and that's perfectly fine. But if one of them is vertical, then it enforces that rule. Or if just the other one is just vertical, then that also enforces that rule. So this is a perfect rule for these lamps. We could also have the case where we have two lamps that are in the same row or same column, and they cross like this. And so in this case, we would say not P1 or not P2. And this will force one of these lamps to be horizontal and eliminate that constraint. So what I do is I just make a rule for every single ij pair. So I look at every single ij pair of lamps. And if they're within striking distance of each other, then I add one of these rules. And so I end up making an implication graph off that. So that's step 1, add all the rules. Step 2, then you just run the two-sat solver. So we just run that strongly connected components algorithm once we build this graph. Okay, so that's the first thing of illumination. I think this is actually a better problem if we remove one of those dumb constraints that were imposed initially. So here's an alternative version of illumination I think is more interesting. So I'm going to say no square can be illuminated twice. And I just remove that extra constraint. So now if I have my graph like this, something like this, I'm not allowing these kind of crossing anymore. So this is an important change in the problem. It makes the problem a little bit more interesting, in my opinion. So if two things are diagonal like this and they're within a certain striking distance of each other, what you need to basically force is they either both have to be horizontal or they both have to be vertical. That's the extra constraint we need to add to this implication graph. And so what you realize here is we need to do bidirectional implication. We basically, if two edges are in striking distance like this and they're not on the same row or same column, but they're diagonally adjacent and they can hit like this, then what we do is we end up adding statements like this to the graph and deal with it that way. So that what this will allow us to do is just add these statements to the graph in addition to the statements we added if they're in the same row or same column. And if that's the case, then we just run the original two-sat solver and we still get the answer. Okay, so let's talk about the next problem. So I have this problem called Piece It Together on Caddis. So you can look that one up. This was used in Northwest European Regional Contest a few years back. Okay, so the way this problem works is, so I'll call it Piece It Together. So I have black, white, 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 black, white, white, black. So we have a grid like this that's partially filled in. And we have some pieces that we'd like to use to color the grid that are something like this. And so what you can see is we can just select certain cells of the grid and basically tile the whole thing with this kind of cell. And you just have to make sure black is in the corner and then the whites are on the far side. And so you're just trying to cover all cells, see if it's possible, yes or no. So one thing you can try a little bit later if you know how to use flow, there's actually a way to solve this with flow. The runtime is e square root v. It's actually a bipartite matching thing. You can run Dinic and get this runtime, and actually runs fast enough. You can use flow. The solution guide to this Northwest European Regional says flow doesn't work, but it actually does because Dinic is really fast on certain classes of graph. But last thing, or the thing I'd like to say is we can solve it with two-sat. And that's the solution I'm going to do. And so that'll be a linear time solution on the number of cells in the grid. And there's also a really mathy solution that will work. So you can look up the guide to this problem from Northwest European Regional Contest, and it goes in detail. This problem has a lot of extra structure. So two-sat's kind of overkill to solve it. But I'm just going to go over the two-sat solution because I think it's kind of cool. And I think it's worth going over. Okay, so we have this problem Piece It Together. The very first thing we have to figure out are what are our variables. And so I really like to show this problem off when I'm teaching two-sat because I think it's not so obvious what the variables are. So if you're watching this video now, one thing I try to do is try to figure out what the variables are yourself before I give this away. So one thing people try to do is they start to think about, and so maybe you try this on your own. Well, for every single grid state that's black, multiple configurations. Or something like that. So there's 4 possible configurations every single black cell can be in, which isn't exactly Boolean, but they start to go down that path and they start to think, okay, if my grid, depending on its truth value, my grid is going to be one of these states. So if it's this kind of state for black, that's one, this is true. And if it's not this state, this is false. And then, so you basically, for every black cell, they start to think, okay, we're going to have 4 variables. I'm going to have this one This is P2, this is P1, this is P3, this is P4. So usually when I'm walking through this in person, this is the first idea people start to have. I just have a different one for each of these states. And then we have this weird problem. If you have P1 be true, then you need P2, P3, and P4 all be false. If you have P2 true, you need P1, P2, P4 to all be false. And very quickly on, you can turn this into a satisfiability problem with these variables, these variable choices like this, but it's not two sat. It's a more general sat. So the issue with this is if you set up your sat like this, and it could end up being just, I think you can do it with 3 sat, but any sat can be represented as 3 sat. That's probably a little off topic, but you can figure out how to set this up as 3 sat, but then you get stuck. So your variable choice matters. That's the point I'm trying to emphasize here. So if you try playing with this in terms of these variables, these are just bad variable choices. And it doesn't lead to a correct solution in terms of 2 sat. So what I'm going to point out is when we have a black cell, there are 2 groupings that matter. Like, look at every single one of these configurations. We're either going to have something below us, in this case, P1 and P2, or we're going to have something above us, in the case of P3 and P4, something above the black cell. So it's this way, or it's this way. Okay. Let's look at another state. It's this way, or it's this way. And if you make one of these choices over here, and then you make one of these choices over here, so it's actually XOR, that's okay. Then this choice mixed with this choice forms a piece. So the trick is to not think of the piece as a whole piece, but to think of this as 2 separate independent decisions. Okay, so what should my variables be? That's the point to describe. So if I ever have a white next to a black, in terms of a piece, well, that's going to be P1. Or maybe there's a white down here, that's P2. So whenever you have an adjacent black and white cell, that gives you a proposition. So one thing we're going to have to do, just like as a specialty check, we're going to have to make sure that every white piece has at least some black piece okay there. All right, so we either need this to be true or we need this to be true, but not both. Well, that's just XOR. And we already know how to represent XOR in terms of 2 sat solver. So I'll just write a helper function when I solve this. That basically I say add an XOR, and it'll call the code to add 2 OR statements. And then that will call the code to add implications to my implication graph. Okay, so that's the first set of constraints. But that's not sufficient. We worry a little bit about cases like this. Right? We don't want to form a tiling like this and then form a tiling like this because it uses that white twice. So we need to also look at every single white cell and look at the black cells around it. And I just look at all the implications. So we have 2, we have 1, we have 3, 4. And so 4 corresponds to this whole piece and so on. So what we need to do is we need to force 2 and 4 not to be used, or 1 and 2 not to be used, or 1 and 3 not to be used. So we have all these different cases. So I want not P1 and P2. So if we ever get the case where P1 and P2 are both true, then that's bad, and we want to disallow that using our two-sat. Luckily, De Morgan's law is a thing, so we actually get not P1 ORed with not P2. And so we get a bunch of these disjunction rules that we can add to our two-sat, and we can get away with adding disjunction rules, which is useful. So we do that for all pairs here. So that ends up being for every white cell, we end up adding 1, 2, 3, 4, 5, 6 different rules, or rules. So that ends up being 12 edges total for every single white cell. So a constant number of extra edges to our graph, but it enforces all the rules for handling two-sat. So you set up that graph, you run it, and then you see if it's satisfiable or not. And that's how you end up solving the problem. Okay. So this is a bit more of a complicated two-sat. So I'm actually going to go try coding this one and see if I can get this working. And you'll get to see how two-sat works. But that's how to solve it conceptually, or you could try coding it on your own. You don't have to watch the coding piece if you don't want. But if you're interested in how to implement this, then that's what I'll do. We'll piece it together. So I've already brought in my strongly connected components from the last algorithms live, and it's also got this graph stuff that should be fairly useful. So I'm going to use both pieces and hopefully make it easier to implement this problem. Okay, so we need to read in the grid. So we're going to have some width and height. And we'll just read in the grid raw. So height is the number of rows. Width is the number of columns. Just read in the grid that way. So I need to put in an inbounds check, I and j, in terms of the grid. So if like that. So that'll come in handy later. Okay, so I need to make my two-sat graph. One of the things I'm going to do is I need directions. So a way to define when I have my variable going up or down or left or right is going to be a cell location. And I'm going to just say wherever a black cell is, cell location, and a direction will tell me what the ID is. So I'm just going to make an ID chart because I need some bookkeeping to keep track of like what pairs of black and white cells lead to what IDs. So I'm just going to make a chart for that. And I'll just call that IDs. And maybe I'll do rows and columns and just do everything in that form. I'll do everything row major order. So that way I don't confuse things. So I'll do height, width, save memory. I'll do each of the 4 directions. So I'll do my dx/dy array trick. So this is a really common trick if you're dealing with directions. You can just store directional information in this fashion. Makes things easier to code. And I equals 0, I less than height, Okay. So I need to add my rules to our rules, but I'm going to do is I want my code to crash if I mess up filling in an ID. So what I'm going to do is I'm just going to make ID labels for every single direction combination. So I need to check out one of these cells has to be black. The other cell has to be white. Other cell. And if that's the case, and the ID that's currently here in this direction, an INJ, is going to be equal to current ID counter. So I'm just going to call that num terms. I think that's probably a good way of doing it. I'm just going to keep track of my number of variables, because remember, I have a variable for every single direction. So initially it's 0, and then I'll just keep track of that. Actually, I'm going to change the way I code this a little bit. So refactor this. So also what I'd like to try to do is if this is what I'm going to do is I'm just going to keep a Boolean. I'm going to assume my code works. And if I fail to pass this test, because I have to make sure that every white cell is at least satisfied. So I'm disallowing multiple. Maybe I add that to my two-stat graph, actually. So at least one of those white cells has to be taken. Think about that. P1 or P2. Oh yeah, so at least one of those gets forced. Yep. Okay, we're good. Okay, so let's add my rules now. So I have all my terms. So I need to make an implication graph now. So I'll just call that G. So I have my handy graph class, very similar to how I did Targens. So I'll do 2 times the number of terms. So the number of terms is the number of variables I have. I just multiply by 2. That gives me my graph size. And now I can start adding those XOR statements. So I'm going to basically reuse a lot of this code. So I'm only going to check 2 directions. I'll join all this. All right. So I'm going to do is I'll just check the vertical direction. And then oops, there should be direction. Slight bug there. Oh, dang. I messed up. 1 sec. Should also be direction. All right, so we also had a question from a viewer where you're saying like talking about the lexicographically first solution. If we want to pull out lexicographically first solution, so what you do in that case is you essentially just force a variable. Remember, if you remember, the P or P will basically force a variable to be true. And so you try forcing the variable you care about, and then you run toSat again to see if it's satisfied or not. And if it's satisfied, you can set that to be true. If it's not satisfied, you have to set it to be false, add that implication to the graph, and then continue on running it. So finding lexicographically first solution isn't too bad. But that's the trick for that one. Although I'm not coding it this time for this case, because I didn't have a problem where I had to pull out lexicographically first solution. Otherwise, I would be coding that. And I would have liked to have a toSat problem where I pull out the answer. This one is just pull out the answer, pull out an answer, not necessarily the answer. Okay, so all I'm doing here is I'm basically setting up this rule, which was the XOR rule. I have white above white, white above black, or black above white. And I basically just want this XOR rule. So what I'm going to do is I'm just going to look for a vertical piece or a horizontal piece, and then just check its complement. And if they both exist, then I add an XOR edge. Okay, so what I'll do is I'll do mi is I plus dr of d. And this should also be these. Fixing my bugs. And then I will do mj. And this is also the IDs. I don't have to Yeah, I don't have to do that. Okay, so those are my two IDs. So I'm just going to write a helper function called add XOR. So I don't actually have to check if that second number is in bounds. Actually, I don't even have to check. Yeah, I don't even have to check anything here. And those negative ones are nice. And make this code really simple. So I already did like inbounds checks. So I know I and j are always going to be in bounds. So I can just pull them out of the ID table, and they'll be -1 if they go off the grid. So I don't actually have to add the edges. So I can just do that check here. And this ends up working out. Yeah, and I always just check the barrier like that. So let's write some of our helper functions for TwoSat, because I think that'll be interesting to see. So what I typically do is I do a negate function. And so I'll do the node itself for P, and then the node plus number of terms for not P. That's how I kind of group things. So it's from 0 to num terms is all the true implications, and then from num terms to the end of the graph is all the not true implications. So yeah, I can just negate things. I can just return also do some modular arithmetic to get it to wrap around properly. I'm going to do it that way. I'll make an add or, so I'll do something like this. That's going to be my add or. So then I'll make an add or function. Remember, I have to add both rules for my TSAT solver to work. And then I can just add implication. The implication is just adds it to the graph. That's all that needs to do. So I have or, XOR, and I don't have to do any variable forcing here. But that works out fine. Okay, so the last thing I need to do is I need to add all my rules for the white cells. Because remember, if it's a white cell, it has issues. I'll just create this instead of creating this each time, I'll just make it once and then clear it. Okay, so here's what I do. If I'm a white cell, then I go through all my neighbors. And life is good. That is also good. Okay, so I have to make sure I'm in bounds, and I also have to make sure that my current cell or my adjacent cell is black. That. If that's the case, I can add that cell's ID to my neighbor cells. So I need to go in the reverse direction, because if I'm going down, then my neighbor is going up to see me. And I just have to get its ID. So I add its ID to my neighboring ID. Now I have to hook up every single pair and then force them to not conflict with each other. And so those are my two IDs. And I just add an OR edge to negation of ID 1 and negation of ID 2. So that adds my OR. And so those were all my rules for the two-sat solver. So that should be my two-sat graph if I set this up correctly. And that should solve the problem. So I've got my two-sat. Now I can run a strongly connected components code on my graph. I'm assuming I'm passing, but if I have a contradiction now, in other words, if they end up in the same strongly connected component, they'll have the same ID. So each element and its complement, if they're in the same strongly connected component, I just say if they're false, then they don't pass. So that's true here. And then I can print out the answer. So we do have some questions from viewers. Let's see what's going on. Yeah, and so the question was, first question was, lexicographically for solution is n squared, no need to code. Yep. So the way I know how to do it is n squared. There might be a more clever way to do it and better than n squared. But I haven't really thought too much about it. So I'll give it some thought and see if it's possible. Shouldn't it be ni and j for num-black neighbors? OK, let's go up here and see if there's a bug. you are 100% right. Very nice catch. That is one bug I would not want to find myself. Of the code. Okay, let's try running this code, see if we can get this problem. Compiled first try, that's always a terribly awful sign. Fails to have a contradiction on test case 2. The test case 2 is like this. We end up having contradictions like this. Okay. So the main thing that's going to cause a contradiction be this code right here. So I'm going to try to debug this, see if I can get this guy working. If it has 6 terms, so 1, 2, 3, 4, 5, 6, so it should have 6 terms. Okay, so 0, 0 just has term 0 in its thing. 1, 1 just has 2 and then 3 in its thing. 2, 0 has 1 and 4 in its thing, and they both can't be true. And then this one just has 5. Okay. So these need to be in conflict with each other, but if one goes off the grid, then I need to force one to be true. That's what I'm not doing here. So remember, I have to say it goes up or down, but if one of them is -1, then yep, that's my bug. I'll actually do a force variable. I'll write an extra function called force variable. And so I could do this as add or, but it would add 2 of the same edges. So I'll just do add implication, and I'll just add the negation of j going to, or negation of I going to I, because that's the same as doing or, because it would just be adding this edge twice, and I only need to add it once. So that's how I do my force variable. Oh, yes. And that's all I have to do code-wise. So I will comment out my debug prints. Give this my first go. Hopefully it works first try. So unlike my usual episodes, I did not code this one ahead of time. We might have a little bit more debugging to do than usual. And I'm going to give this a submit and see if I get it. Should be very suspenseful. Ooh, wrong answer. So let's see if we can figure out a test case that breaks this. Nice small test case. Probably tests better anyway. Something like that. So I'll do that. Add some baseline tests. So P3 was not possible, that's true. P4 is not possible, that's true. P5 is possible, that's true. So I'm losing out there. So I also should probably check to make sure every black neighbor has at least one white neighbor. Yeah, so you should always test your boundary cases. That's the important rule here. That was poor testing on my part. Okay. So that should fix that case. So if I have an isolated black cell, that's not allowed. Still passing those cases. So let's try submitting again. See if I get a little further the tests. Oh, I got a little bit further. Should probably make even better tests. Okay, so that's a problem. Let's print out some stuff every time there's an or statement. Okay, so I have this vertical piece here, these horizontal pieces here. So I need either this to be true or this to be true, or I need this not to be true or this not to be true. Okay, that seems reasonable to me. So I need either this to be true or this not to be true, or this not to be true or this to be true. Okay. Oh, and I need at least one of those pieces to be true for W. So I need to force at least one W to be true. Last case. So setting this up as a two-sat graph. Apparently missing something in terms of my two-sat. See if I can fix it. So it should be connected to at most one black cell, but it needs to be connected to exactly one white cell. See if I can read the problem again and see if I'm not mistaking anything. All right. I think I need to I need to also check a parity check because I can't force everything to be true. So I can't force at least one to be true. So I have to make sure the number of white cells and number of black cells line up. Let's see, grid ij is white, num white gets added. So one last check there. And this will ensure that everything lines up. All right. So that's that last piece of debugging. Let's see if I get it this time. Ooh, still a wrong answer. See if I can get a good test case that breaks me. I Seems to work just fine. Let's do one more. I think this one has two sat. Very interesting. Very tricky bug to find. See if I can figure out this case. Six, seven. You can catch this bug. Small chance of the bugs in the SCC code, but that would be a shame. Think about it. See if we come up with a better case. See if we can debug this. Two, three. I believe I found the test cases, so I'm going to see why this code breaks. Oh, that's bad. White, black, white, like that. Oh, yes, I have a bug. So I don't need to just check if I have a neighbor. I need to check, hold on. This was the wrong way to do this check. Okay, so here's the bug. The bug was basically, if I have a black cell, I need to ensure that I have at least one positive, or at least one vertical piece and at least one horizontal piece. So this is a special case. So if I don't have any vertical pieces, then I have a problem. Or if I don't have any horizontal pieces, then I have a problem, and not if I'm completely isolated. So that was the test I needed to make. And now that case is no, but the rest still work. See if we can get it now. Seems to be working. All right, let's see if there were any more comments. Yep. Let's see if we get this one right now. Okay, and that's how you solve that problem. So one thing I want to point out about 2SAT that I think is kind of interesting when you go into this kind of problem is there was a very clear way that we could force no pair of these to be true. But the thing that was interesting is I couldn't force at least one of these to be true. And so that's why I had to put in extra constraints into the problem as far as making sure the number of white cells was at least twice the black cells, because it basically forced an extra condition on there, so I don't have to handle that second condition. And I also had to do some manual forcing pieces to reduce it into the 2SAT and then just run it into the 2SAT solver. So sometimes when you're doing 2SAT, you need to do a little bit extra work on top of just the 2SAT to get it to work. But the 2SAT's great for certain constraint solvers. So if one good thing to do is if you look at the blog post, there's several problems involving 2SAT. So I'd say give a few of those other ones a try. They're good practice. There's one from CodeJam. There's one from Southwest European Regional Contest. You can solve this Pacific Northwest ICPC problem, that Illumination Problem. That's a good first 2SAT problem if you've never done this before. So I hope you enjoyed this talk on 2SAT, and I hope that you can learn something there. It's a much longer video than normal, given the nature of the live coding and the difficulty of this problem. But I'll see you guys all next week for another Algorithms Live episode. I believe next week's episode will take place on Sunday at a unique time. I'm going to be helping with a training camp for programming contests over the next 2 weeks, so that'll be taking most of my time. But I have a kind of interesting problem I think I want to share for that Tuesday episode, and it'll be a much shorter episode, but still be pretty interesting. So tune in then, and I'll see you guys next week.